Another parameter that we can calculate is what we call the packing efficiency of a crystal. For packing efficiency of a crystal, it's basically just the volume of all of the atoms divided by the volume of the unit cell multiplied by 100%. So in the case of FCC, for instance, we have 4 atoms for every unit cell. Therefore, the packing efficiency will be equal to 4 multiplied by volume of the atom divided by volume of the unit cell, which is A cubic, times 100%, or this is going to be equal to 4 over 3 pi r cubic. This is the volume for a spherical atom divided by the A cubic, and for FCC this is going to be equal with the 22.63 r cubic multiplied by 100, so the packing efficiency will be equal to around 74.05% of packing. You can also calculate this for BCC, where you have 2 atoms for each unit cell, and for SC or simple cubic, where you only have 1 atom for each unit cell. The relation between A and R we have discussed in the previous video. So what we have discussed so far is crystal structure, and this makes up the crystalline material. Crystalline materials are the materials that is arranged or ordered in a repeating manner, just like what we have discussed for the simple cubic, BCC, and also FCC. And another thing, we also have the amorphous material, and this one is not arranged or not ordered. We have focused our attention on discussing about the crystalline materials, but we also should know that there are materials in nature that do not have such arrangement or some kind of order in a repeating manner, and this is what we call the amorphous materials. Finally, we'll discuss about bonding and solid, and we'll pay attention to metals, insulators, and semiconductors. As we have known in the chapter 1, metals are malleable, meaning that they can be formed into useful shapes or foils. Metals are also ductile, meaning that they can be pulled into wires, and especially metals are conductive, so they are good conductors of both electricity and also heat. We have discussed in chapter 1 the model of sea of electrons to be able to visualize the structure of metal bonds at the molecular level. Now say we have a lithium metal. Lithium metal has a valence electron in the 2s orbital of only 1 electron. Now, if we have a bonding between 2 lithiums, then we would have 2 orbitals, and both of the electrons will fill in the lowest energy possible. So in this case, a pair of electrons at the orbital with lower energy. Now, if we have 4 lithium metal together, we will then have 4 orbitals, and it splits into 4 different energy. The 4 electrons from all of the lithiums will fill in again the orbitals at lower level. And now, if we have N of lithium, we will start seeing that the orbitals have merged into a band that is filled by electrons that we call the valence band. And another band at the top part that is not filled by electron, and we call this the conduction band. And here is the origin of the term of band theory that is used to explain bonding in metals and also semiconductors. Now, the relation between band theory and conductivity is as follows. For a compound to be conductive, that means the electron should be able to excite from the valence band to the conduction band. And we can see in metals such as lithium like this. The valence band and the conduction band are very close together. They're very much adjacent to each other. So the electrons will be very easily jump from the valence band into the conduction band, resulting in a conductive materials. Now, if we to compare the bands between metals, semiconductors, and insulators, we can see as the following. For metals, the valence band is very close together with the conduction band, so the electrons of the valence band can easily jump to the conduction band. However, at the other hand, we have insulators. For insulators, the gap between the conduction band and the valence band is very prominent, so there is no way for the electron to be able to overcome this gap to jump into the conduction band, and therefore insulators are not conductive. And in the middle, we have the semiconductors, with silicon and germanium being the most prominent example, where we actually also still have band gap between the conduction bands and the valence band, but the band gap is not that huge, unlike the insulators, so it still is possible for the electron to jump from the valence band to the conduction band. If we put enough energy, or if we, for instance, give heat into the system, then the electrons would possess enough energy or sufficient energy to be able to jump from the valence band into the conduction band, and therefore the semiconductors will become conductive. Another way to help the electrons jump from a valence band to a conductive band is by doing what we call doping technique. Is adding a trace amount of other materials or other elements into a semiconductor. And from here, we can have two types of doping. We can have the N-type doped system. We can have a P-type doped system. Again, we can draw the conduction band and the valence band for the semiconductors. For the N-type doped, we introduce a certain metal, so a different metal, for instance, like arsenic, As, or phosphorus, so the guys from group 15. And in this case, they have extra electron in comparison to germanium and silicon. They will become a donor of energy. So donor of energy. And we will have an extra energy level over here that is just below the conduction band. And the energy level will have also electron over here. And now this electron can overcome a smaller band gap to jump and become a conductive materials. On the other hand, for the P-type system, we dope the germanium or silicon with group 13 like the gallium, so from group 13. And because they are lacking of electron in comparison to group 14, it will instead provide an acceptor energy level. So acceptor energy level. which is empty. And in this case, electrons from the valence band can jump into this empty acceptor energy level and overcome a way smaller band gap in comparison to the initial band gap that is larger. This one is what we call the N-type doped semiconductors, and this one is what we call the P-type doped semiconductors, depending on the element or extra element that we put in a trace amount to be able to provide either a donor energy level or an acceptor energy level to make the excitation of electron become easier and the materials become conductive.